Morning. How's everybody? How are you, David? I see you over there.
I'm fine. Do you know if these three are still assigned in or?
Well, as of yesterday they were. So as of
Okay.
yesterday, I don't know. Maybe they'll come in today. Yeah, I don't know. I'll send them an email and see if I can get a reply. But as of yesterday, they were still in.
Okay.
Okay. Thank you. Okay. I'm going to go ahead and pass back tests over here, and we'll talk about them for a few minutes. Some of you were laughing when I said I was going to pass back tests. Let me say just a little something, okay, because the test, I know many of you did not score where you would like to score. Being a first test, it usually is probably the toughest because you don't really know what to expect. You don't know what I'm looking for. We've had a lot of material in this Chapter 6. We do want to remember our Chapter 6 material, though, so if you did not, get where you really need to be on this test, please go back over the test. Please take it to the CFAA. Come see me. Get with somebody else. Do something so that you can be up on what you missed, because we still use this information throughout the semester. Okay. Now, with that said, there's still plenty of time to make whatever grade you would like to make in this class. So I don't want you to give up on me as far as that goes, but there's still time to get the grade you would like to have. Let me pass these back and we'll talk about them for a little bit, okay? And we'll go from there. Let's see, Rachel McCauley. Juan Gisbert. Tom Zaleski. Evan Riley. Chance Pritchett. Larry Moore. Brandon Delgado. Cindy Lawson. Jonathan Beck. Here. Jacob Porter. Here. That's the fourth here. Amelia Kowalska. Stephen Schuyler. Gerald Rivers. Amy Spencer. Tom Ellsworth. Zach Stillman. Veronica Moore. Aaron Mayer. Kyle Seavey. Clay. I thought someone was wrong. No. There, okay. Brent Rathbun. Jamie Kinchler. Did everyone get their test back? Okay, so we have the test here for a moment, and also, let me say something else. I had to turn in early semester progress grades yesterday. Those were due yesterday, and yes, the bulk of those is this test. I did look to see if you've been on your My Math Lab working on that sort of thing, but overall, the test is the bigger thing. So if, again, they make us turn those in really early, okay, I'm just going to say it's a little bit early for that. I only have the one test grade and a little bit of My Math Lab. So don't panic. If at any time, though, you want to know what your grade is, let me know, okay? Still time to bring the grades up, to pull out of whatever. So some of you did really, really well, and some of you not so well on this one. But let's look and see where some of your mistakes were for just a moment. I don't want to spend a ton of time on it, but I do want to spend a little bit of time here with it. So does somebody have a question you would like to ask about from the test? Okay, number 5. Let me go down to 5 here. Number 5, we have the cosine of theta is equal to 2/3, And the tangent of theta is less than 0. And we wanted to find the sine of theta. Okay. So on number 5, we have a little bit of information given, enough to let us know which quadrant our angle is ending in. Which quadrant would we be in if the cosine is positive, but the tangent is negative? Quadrant 4, right. So we're in quadrant 4 is what that information tells us. That's where the angle is ending at. But we choose to look at a corresponding angle right here, theta, to work with. And what we know about that then is the cosine is 2 over 3, and cosine is equal to x over r. So that tells us x is 2, r is 3. We will have to find y. Okay? We'll have to find y. How do we find it? We use that x squared plus y squared equals r squared. So we have 2 squared plus y squared equals 3 squared. That would be 4 plus y squared is 9. So y squared is 9 minus 4, which is 5. And that makes y be the square root of 5. But I look at where I am here. It's got to be negative square root of 5, right? Because I'm in the 4th quadrant, so the y value has to be negative. So now we want to know what the sine of theta is. And the sine is equal to y over r, so that has to be the negative square root of 5 over our r value of 3. Okay, so that's what we were looking at there. Is there a question on that one? Question about any of the work on that one? A lot of excuse me, number 1A and most of number 2 was about the unit circle. You got to know that unit circle. You want to keep that information. 1B, you had to use the conversion formula and multiply by pi over 180. Okay. Number 3 was similar to the one we just did. X squared plus y squared equals r squared. You can never assume that you're in a unit circle unless you're told that, or unless you know it's one of those angles that we've looked at from the unit circle. Okay. 4 was with the identities. Go ahead. You had a question?
Can we do number 8? I'm not too sure what phase shift means as far as where it fits into the equation.
Okay, so we're going to go over to number 8 and look at how the phase shift fits into the equation there. Yeah, a lot on this back page then was with the graphs, the arc length. Well, the first one was arc length and area, and for that one you had to remember for arc length and area that you want your angles to be in radians. Okay, that was part of our stipulation on the formulas. 7, we had a formula and picked out amplitude, period, and phase shift. And then we got to 8, where we know that the amplitude is 2, the period is 6 pi, and the phase shift is pi 6th. And we want the equation of a sine function. So y equals a sine omega x minus phi. Okay, a sine omega x minus phi. All right, so we knew that 2 went there. That part was, I guess, pretty obvious on that part. But what about the rest of it? That's where it gets a little tougher. We know period for a sine function is equal to 2 pi over omega. We also know that period for this one is equal to 6 pi. So that tells us that 2 pi over omega has to equal 6 pi. That those two things must be equal. That's 6 pi over 1. So if you want to cross multiply, that makes it maybe a little easier to see. We'll have 6 pi times omega equals 2 pi. And to get omega, we'll divide both sides by 6 pi. And we see omega equals 1/3 because the pi's cancel and 2 goes into 6 3 times down there. So omega is 1/3. So now we would have y equals 2 sine 1/3 x minus phi. That's what we know so far. Are we okay so far? Okay. Phase shift. Phase shift is phi over omega. We know that phase shift is pi 6 for this one. Okay. So we've got to have phi over omega equal to pi 6. But the thing here is we already know what omega is. So omega, it was 1/3. So it's phi over 1/3 equals pi 6. right? We already found omega was 1/3. So we're going to cross multiply. We'll get 6 phi equals 1/3 pi. And I've set that product equal to that product. That's what we're doing there. Divide both sides by 6. Phi is equal to 1/3 pi divided by 6. That's the same as times 1/6. So that's going to be 1/18 pi. Okay. So now that tells me my equation is going to be y equals 2 sine 1/3 x minus, and phi is that pi 18ths or 1/18 pi. So it just goes in for that. The minus stays there. If it come out to be phi equals negative 1/18 pi, then I would have had minus negative 1/18 pi, making it a plus in the equation. We were told already our phase shift was pi 6. Remember, the phase shift number itself is what makes that part in parentheses equal 0. Remember that? We were looking at it the other way, and we were taking the argument and setting it equal to 0. So if I were to put this value, pi 6, back in for x, up here in my equation, in this final equation here, if I were to put that pi 6 over here in for the x because of how we solved before, then I would see that that part in parentheses would give me 0. Okay, and we need that to happen in order for it to work on the phase shift there. So whatever you got for phi is what went in for phi in the equation, with keeping that general form of the equation. Questions there? Are we seeing it a little better looking back at it? Is that helping a little bit? I hope that's helping out a little. Now, some of you gave me a lot of blank problems, okay? And there's not a whole lot I can do with blank problems, but just, be sure and look back over those and see what happened. Did you just freeze up on the test? I don't know. I don't know if you just froze up or if you didn't study enough or what was going on with it, but look back at those for sure. What else from the test? We'll look at maybe one other one here. Yeah, go ahead. Number 10. And what was yours? I saw a hand up over here too. Okay, so we really want 9 and 10. Okay, let's do 9 and 10 then. 9's pretty quick actually, so I'll go there first. What makes f of phi equals cosecant phi undefined? We talked about these functions being undefined whenever the denominator was equal to 0. We know that cosecant theta is the same as 1 over sine theta. So whenever sine is equal to 0, then this function is undefined. So whenever sine equals 0, cosecant theta is undefined, right? Because we cannot divide by 0. So our job is to figure out where that happens. Where does the sine equal 0? Where does the sine equal 0? Okay, and we typically like to answer in radians though on this. So the sine is equal to 0. Let me draw the unit circle here just a moment. Remember, we have these coordinates here. 1, 0, 0, 1, negative 1, 0, 0, negative 1. Okay, so where's the sine equal to 0? It's when the y value is equal to 0. So it is at values like 0, pi, 2 pi, right? And it would also be the negatives of those. And the way we talked about that before was we said it was that integral multiples of pi. All the integer multiples. You could say integer multiples, integral multiples. Okay. So that's when it's undefined. Whatever causes its denominator, even though we look at cosecant theta, we don't see a denominator. We have to think about the fact that it is 1 over the sine of theta. And number 10, graph y equals negative 4, cosine 2x, sketch the graph, at least one period, make sure it goes through the correct x and y intercepts, and state the amplitude and period. So the amplitude and period. The amplitude is 4. It's going to be the absolute value of negative 4, which is 4 out there. Period is 2 pi over the omega value. The omega value here is 2. So 2 pi over 2. So the period is pi. Okay. which means when we get on the graph, then we have to reflect this information up on the graph. We had it marked like this on the sheet, things like that. It's going to have to go up to 4 and down to -4. This one's actually going to have to start down on the y-axis at that -4 area. It is a cosine graph. So, but also the period's just pi. So halfway through the period is where we have the curve. There's one period of the graph right there, okay? It's going halfway between 0 and pi. I mean, it's cutting halfway between 0 and pi halves, but pi halves is there between 0 and pi. And then it would come on up. So if you look at it, it's something like that. I had to be able to see on your graph that you had the period equivalent to pi units so that you understand whenever you say the period's pi, you can draw it to where the period appears to be pi. Okay. If you got the amplitude and period, I think I gave you 4 points out of 10 if you did not get the graph. Okay. And I tried to be pretty consistent there. Secant squared theta minus 1 is equal to tangent squared theta, by the way. Because tangent squared theta plus 1 equals secant squared theta. So that was off one of our Pythagorean identities. Anything else about the test in general? They were 10 points each. They were split up into parts based upon, you know, the parts that they had within them. Any other questions there? If you have other questions you want to ask me, you know, stick around after class and I'll be glad to answer, okay? All right, you all may keep those, and please go back through them. I just highly recommend you go back through those. Let's go forward now. All right, here's the other deal. Let me give you this other little deal first, too, before I forget it. I was about to forget. Toward the end of the semester, there will come a day. I don't know what day, but I'll let you know ahead of time. I'll give you a chance to retake one test out of our chapter tests. It can be this one. It can be the second one. It can be the third one. I think we have 3 tests and a final in here, right? So you can pick one to take on that particular day. Okay, I won't be doing makeups or all that junk. You know, it'll just be a one-day offer. So I usually do it at the very, very end of the semester before final exams, but I don't have the date set up yet. Okay, but I'll let you know. But that gives you a little bit of, oh yeah, I can go back and do something about this. Some of you will want to do that. Okay. Everybody understand? That's a good deal, right? I hope so. We're not doing it right now. We'll do it at the end of the semester. Which actually, that's going to help you even more because we're still using this stuff throughout the semester. Okay? I think it's going to be more helpful. Let's go back to chapter 7. What do you remember about chapter 7 from last week?
We're doing inverse functions of sine, cosine, and tangent.
Right, we're doing inverse functions. Sine, cosine, and tangent. Inverse functions, right? What does that mean?
It's across a 45-degree angle. It's y equals to x, cross y equals to x. It's
the what now?
Tell
me that again.
It's mirrored across y equals to x.
Okay. Whoops, I'm sorry. So when we talked about inverse functions, we talked about several properties of those starting out last Thursday. So if you missed last Thursday, you'll want to go back and double check these properties. But several things. One, when we have inverse functions, if we were to graph them, their graphs are symmetric about the line y equals x. Okay, we know that much, right? Let me just put some of these things back up here for a minute. So we might want to use some of this today. Inverse functions. Graphs are symmetric about the line y equals x. Another thing we said about inverse functions was they're composite functions. If we do the composites, f of f inverse of x, it's equal to f inverse of f of x, and they're both just equal to x. Okay, so when we do the composites in either order, we just get out the argument there, or whatever the x is. Okay, what we're actually saying there is that the function and the inverse undo each other. It's like they undo each other. And I think we gave the example last week, the square root of x squared. The square root and the squared undo each other. Okay. Third thing is the domain of the function will be equal to the range of the inverse. And the range of the function will equal the domain of the inverse. What that means is that their x's and y's in their ordered pairs get switched. If I have 2, 3 as a coordinate or a point that's a solution in the function f, then 3, 2 will be a solution for f inverse. Okay, they get swapped out. Seems like we had another one. Let me think what it was. Did we have another one? Well, that's all I'm remembering right now, so we'll have to leave it at that for the moment. Okay, graphs are symmetric, the composites are equal, and they swap domains and ranges. We did also talk about them being about a function being 1-to-1 if we were going to find its inverse. Okay, so what did 1-to-1 mean? Right, not only are no x's repeated, like from the function, also no y's are repeated. So I'm going to put here no x's or y's repeated. And where a function always passes the vertical line test, a 1-to-1 function also passes a horizontal line test. So it passes both vertical and horizontal line test. So we were talking about our inverse trig functions, namely sine, cosine, and tangent last week. And because none of those are 1-to-1 functions, we're cutting them off at certain places to make them be 1-to-1, to only look at a portion of them that are 1-to-1. This is just a universal cutoff point, okay? It's not something I made up. It's a universal cutoff. So that if we were looking at y equals inverse sine x, we said for that one we're going to look from where to where? Right, negative pi halves to positive pi halves. Inverse cosine x. The inverse cosine x is from 0 to pi. And inverse tangent x was also from negative pi halves to pi halves, but not including the endpoints because the tangent is undefined at those endpoints there. So that's what we looked at last time. We kind of showed it on a unit circle idea here as to which quadrants we would be focusing on. We said inverse sine is in these two because it's negative pi halves to positive pi halves. Inverse cosine is first and second quadrants. And inverse tangent was the same as inverse sine. As far as where those angles are falling or where we're looking for answers. Inverse questions are backwards questions for us. Instead of saying the sine of this angle is what, and you're looking for that coordinate, now we're looking for an angle. So if we have a question that asks about an inverse function, we're actually looking for the angle itself. So for example, when we had something like inverse cosine negative square root of 3 over 2, that means what angle from 0 to pi, we have to put that part in there, what angle from 0 to pi has a cosine value of negative square root of 3 over 2? 30 degrees is not the answer. It's a negative value. It's a negative cosine. Look, negative square root of 3 over 2. Where do I have a negative square root of 3 over 2? Where? Nope, not that. 5 pi over 6. Okay, that's the winner right there. 5 pi over 6, right? Look at your unit circle, okay? Look at your unit circle. If I go over to where I have the coordinates, negative square root of 3 over 2, 1/2, That's the angle I should be getting right there. Is that 5 pi 6 on your unit circle? Because that's where the cosine, or the x value, is equal to negative square root of 3 over 2. So I'm asking here, what angle, and since it was an inverse cosine, we're looking from 0 to pi. What angle has a cosine value of negative square root of 3 over 2? That's what we're looking at. That's the question being asked here. Okay. Are we seeing it? Okay. I think we better try another one. All right, so let's do inverse sine. Let's do inverse sine of negative square root of 3 over 2. Now we're saying what angle from negative pi halves to positive pi halves has a sine value of negative square root of 3 over 2. 5 pi over 3. Problem with 5 pi over 3 is that it's out of the range of 0 to, out of the range of negative pi halves to positive pi halves. See what I'm saying? It's negative pi thirds. Okay. Our coordinates there are 1/2 negative square root of 3 over 2. Okay. We have to answer negative pi thirds because we got to keep it between negative pi halves and positive pi halves. So is that the same as 5 pi thirds? We're ending at the same place as 5 pi thirds, but we don't want to answer 5 pi thirds. Okay. On these inverse trig functions, we got to keep it within the parameters that we've set forth. And we were looking at these last Thursday. Y'all forgotten a little bit about these since last Thursday? What's that, Brent? Sine, we are in the fourth quadrant, yes. But we have to be from negative pi halves to positive pi halves. And 5 pi thirds is greater than pi halves. Does that make sense? Yeah. The number itself is greater than, so we don't want to answer with that. Okay, you're welcome. But negative pi thirds falls within those parameters. I know it seems silly, it seems picky. Remember, we're doing analytic trigonometry now in this chapter. We're analyzing things. Okay, we got to think analytically here. All right. Let's see what else we have then. Question? Any other questions here on this page, the screen? We better do an inverse tangent, I guess. Inverse tangent of 1. What angle from negative pi halves to positive pi halves has a tangent value of 1? Pi fourths. That's correct because the coordinates at pi fourths are square root of 2 over 2, square root of 2 over 2, and we know that tangent is the y over the x. So in order for the tangent to be 1, the x and y must be the same. Is there a question there? So, did y'all try some of these from the textbook over on page 446? Anybody have a question from page 446 there? Especially right now, we're looking at ones like the first part, like 13 to 23. Does anybody have something in that part you wanted to look at? Yeah, go ahead.
I had a question on number 43 when we get there.
Okay. All right, we're getting there, okay? All right. Well, heck, let's go on down to 43. This is getting into those composite functions, okay? Remember the last thing that we did last Thursday was talking about when we had f inverse of f of x or f of f inverse of x, just getting x out if it was in the correct parameters that we've defined the function at. So on 43 tells us we're looking at the inverse tangent of the tangent of 4 pi fifths. Whatever this outermost function is, here it's inverse tangent, that tells us what values we're looking between. Since it's inverse tangent, we're looking from negative pi halves to positive pi halves. Normally we think here, when we have an inverse right next to the function, we think of them undoing each other and just giving us this answer right here, the 4 pi fifths. Problem is, though, that answer has to be between the parameters in order to be the answer. And it's not, right? It's too big. 4 pi fifths is almost pi. It's almost 5 pi fifths. Are we clear on that part? It's too big. All right, so what we have to do, let's think about this a minute. Let's go down here. 4 fifths pi, we said that's almost pi. Okay, that's almost pi. What kind of tangent do we have there? Positive or negative tangent? Yeah, it's negative. I don't know what the tangent is, but I know it's negative. How do I know it's negative? Cosine's negative, sine's positive. We have a negative x, positive y, right? Over there, so the tangent has to be negative. Which other quadrant will I have a negative tangent in? In the fourth quadrant, correct. Over here, there's going to be some corresponding angle that also has a negative tangent. Now I need, since I'm on inverse tangent, I need an angle between negative pi halves and positive pi halves that would have the same tangent value as this 4 pi fifths. So what's my angle going to be? It's going to be this one we're looking at right here. What is it? Too big. Past pi halves. It's negative pi fifths. That's right. Actually, it would make it easier if y'all start thinking about it being negative pi fifths. That's easier than thinking all that 11 pi whatever, or, you know, going all the way around like we were before. Now, here's what we're seeing here. We have 4 pi fifths, right? Everybody see up on the screen, 4 pi fifths. This little piece here where I've got the arrow has to be how much? Yeah, this little piece here has to be 1/5 pi to get all the way over here to pi. That being pi. All right. If this little piece here is 1/5 pi, remember from geometry way back, you have these angles across from each other, vertical angles, they're congruent. Okay, so if this is 1/5 pi, then that's 1/5 pi. But we have to say it's negative pi fifths because of the way we're measuring the angle down below the x-axis. Okay, so that's how we're getting that value. So our answer here is negative pi fifths.
Can you do number 39?
Yeah, we look at 39. Are y'all with me on this one on 43? Is everybody with me there? All right, so let's go to 39 then. Inverse tangent of the tangent of negative 3 pi eighths. So this one also, the outermost function's that inverse tangent, and we're going from negative pi halves to positive pi halves, right? Okay. And we want to do the tangent of negative 3 pi eighths. Okay, we don't know what the tangent is, but normally we want to come out here and say, since these two functions are undoing each other, our answer is just this thing if it's between those parameters. So is it or isn't it? That's a question there.
It is.
It is between the two parameters. So actually on this one we can just say that it is this value because it's between the parameters here. Negative 3/8 pi. It's not quite negative 4/8 pi. Negative 4/8 pi would be negative pi halves, right? So we're within the right parameters here to use that value. Now on the previous one though, we were out of those parameters, so we had to get something that had the same tangent value as that one would have had. Does that make sense? If it's within the parameters, we can just say it's that number when they undo each other. Does that make sense at all? Was that yes or no?
That's a yes.
Yes, okay, I'm sorry, I couldn't hear. Does that make sense, Cheyenne?
Yeah, it does. I see what you're saying now.
So if this number is within the parameters, then we use it. But if it's out of the parameters, we have to find an angle that would have the same trig function value and use it. That's within the parameters. Now, with that being said, we didn't get down to that next part yet, but let's put something up from there where we start with the actual function itself, like on 46. Now we've got the cosine on the outside part, the inverse cosine on the inside. My outermost function here is the cosine, not the inverse cosine, the cosine. The outermost function determines where we're looking for our values. This time, this problem says we're looking for the cosine of the angle that has a cosine of -2/3. Okay, does that sound a little redundant to you? The question inside the brackets says, the question inside this part right here says, what angle has a cosine of -2/3? Well, whatever that angle is, now you want the cosine of it. So it makes sense the answer should be 2/3, right? You're going around in circles is what you're doing here on all these. One's undoing the other. Go ahead.
So where we got the cosine on the outside of the brackets, what that means is that it can be anywhere on the circle.
It can be anywhere on the circle, that's true, but what's the range of values? We still have to confine it to some values because we're actually looking for the cosine of an angle, and the cosines only went from where to where. We're not looking for an angle this time. We're looking for the value of a cosine.
Okay. I was thinking that that was only for the inverses, but I see what you're saying now.
So what values do we have to be between to get a cosine of an angle?
0 and pi.
We're not looking for an angle. We're looking for a cosine value. Before, and we were on the unit circle, when I asked you for the cosine of pi fourths, pi thirds, pi sixths, pi sixths, pi, any value on that unit circle, I asked for the cosine of any of those angles. All the cosines stayed between two values. From where to where? Maybe it helps to think of the graph of cosine. It was a wave, right? No matter what I put in, what values did I get out? From where to where?
Be between the amplitude.
Okay, so what does that mean? I've got real numbers there. What are they? From where to where?
1 and -1.
1 and -1, right. So this would be from -1 to 1. Whatever we get out of here, we're doing the cosine of an angle. So whatever we get out is going to be between -1 and 1. Now, before we were talking about the inverse cosine on the outside. Remember, you always work from the innermost part out. So here we're saying, okay, if we were actually getting values, we would work from that innermost part, and we would work our way out to where finally what we're doing is taking the cosine of some angle. Our cosine values always came out to be anywhere from -1 to 1, including those values. Are you with me? Cosine always comes out to be between -1 and 1, including those values. On the previous problems, we were looking for angles, and we had to follow our parameters for our inverse trig functions. Now we're just following what values we can get out for a cosine. So again, though, if this value, because remember cosine and inverse cosine are going to undo each other, right? The function and its inverse undo each other. So whatever this value is in the parentheses, the argument here, if it is from -1 to 1, if we have cosine on the outside, then we're good. That's our answer. Does that make sense? That would be our answer. -2/3 works. It's in between those values. Remember what we're saying here. This part's saying what angle has -2/3 for its cosine. Okay, we don't know the answer to that question, okay, but that's what it's asking us. What angle has -2/3 for its cosine? And then when we put this part out here on, we're saying we want the cosine of that angle. Whatever that angle is, we want the cosine of that angle. You see what I'm saying there? That's why I say we're going around this circle. I want the cosine of the angle that has a cosine of -2/3. I'm repeating myself when I ask this question. I want the cosine of the angle that has a cosine of negative 2/3. I've already told you its cosine's negative 2/3, right? Okay. Kind of we're going in circles when we do the function and its inverse. What if it starts with sine on the outside? What's the range of my sine? We're looking at the y values here. We're looking at what we can get out for a sine. I said cosine had to be from -1 to 1. Sine.
It's also going to be negative 1
It's
to 1.
also going to be -1 to 1 because the sine, the curve, you know, looks the same as the cosine. It still goes from -1 up to 1. What if it starts with tangent on the outside?
It'd be -1 to 1, not including -1 and 1.
Think about your graph of a tangent.
Oh,
Negative infinity to positive infinity. Remember that graph? Okay, I'm going to air draw here. Okay, so I'm trying to draw it from your direction. But it goes down to negative infinity and up to infinity. So it can be anything. Now, what if I have a value inside my parentheses and I'm working with sine or cosine here on the outside, but it's either below -1 or greater than 1? And they give you some like that, of course, also. Like number 50 here. 50 is the sine of the inverse sine of -2. So this one's saying, I want the sine of the angle that has a sine of -2. I note that sine is on the outside. Whatever that outermost function is determines where my answer needs to be. Okay? This one tells me my answer needs to be from -1 to 1. Problem is, when I undo the functions, I'm getting -2. So the innermost question here is, what angle has a sine value of -2? Think about all we know about sine function. Did any angle have a sine of -2? No, none of them did, right? So there's no way to get an answer for the innermost part, so we can't go really any further. So this one, we say it's undefined or not defined. The textbook says not defined. They say if there is no value, say it is not defined. There's no angle with sine of -2. Okay. So on this one, we don't have to try to place it somewhere else like we did with the inverse functions on the outside. If it's just the function itself on the outside, we don't place it somewhere else. We just say it's not defined. If it's not in those parameters, forget it. And what about this one here? 48. Tangent of the inverse tangent of -2. Yeah, we said tangent could be anywhere from negative infinity to positive infinity. So it's going to be equal to -2. So whatever that number is, it just came over. Because it's a tangent, though. Questions?
Well, all of the ones that are tangents remain the same since they can stay from...
Right. That's correct. Yeah, so if they start with tangent on the outside, you'll get whatever that value is there. Okay?
Why did we get cosine?
I'm sorry?
Why did we get cosine?
Why did we get cosine the same? Was that on this one here? Because the value we had was between -1 and 1. But if this value, that -2/3, if it had been -2, -4, 5, whatever, then we would say not defined. If it's outside of -1 to 1. But tangent, we can use whatever it says because tangent goes from negative infinity to positive infinity.
so like if we had 2 cosine of 2 inverse cosine of -2/3, it could be between -2 and 2.
If we had a 2 out there, yeah, we're not going to have that. But yeah, they're just working with these properties of the inverse functions, the function of the inverse of the function here, just to get kind of those properties of the inverse functions. So some other things we want to do with inverse functions. We want to be able to figure out what the function's inverse would be. If we have an equation, we want to be able to get the inverse. And we also want to be able to solve equations that involve inverse functions. So we need to do a little bit of algebra. We've been doing some analyzing here with this stuff. What we've been looking at is analyzing. Now let's do a little algebra with it. Okay. So if I go over here, let's start out with just a basic algebraic equation. Let's say f of x equals x squared. But I'm just going to let x be greater than or equal to 0, so I'm making it a 1-to-1 piece of that function. I'm just looking at the right half of my parabola for y equals x squared. And I want to find f inverse. Okay, for f of x equals x squared. There's some steps we follow to do that. Whether we're working with a trig function or an algebraic function, whatever it is, we're going to follow the same steps. First step is this. We're going to change f of x to y. It just makes your life a little easier there. So let's come over here and do that. Y equals x squared. We're trying to find the inverse function for y equals x squared. Second thing. Remember we said one of the properties of inverse functions is that their x's and y's change places. So we're going to interchange those x's and y's. So I'm just going to say switch x's and y's. So now I'll have x equals y squared. If I do that. Third thing. I want to solve for y. That means get y by itself. How am I going to get y by itself if x equals y squared? What am I going to do? Somebody's saying it.
Take the square root of x.
Take the square root of it. So both sides, right? Square root of x equals the square root of y squared, which gives me y equals square root of x. And fourthly, what you get when you solve for y is the inverse function. So actually what we're saying here is f inverse of x is equal to the square root of x. So the inverse of y equals x squared would be y equals the square root of x. We were only looking at that right half of y equals x squared. And if you recall, here's what y equals the square root of x looks like. And they're symmetric. I'm having trouble drawing it in, but they're symmetric about the line y equals x. Okay, those both should be some familiar functions that hopefully you remember what they look like there. But something like that. So we were able to algebraically go through, follow the steps, and find the inverse function for this one. Questions on this one, on following the steps? Because what we want to do now is get a trig function, a trig equation, and use the same steps to find the inverse. All right, let's find one here. This is 54 off of page 446 as an example. It says f of x equals 2 times the tangent of x minus 3. And what they're telling us out here is that x is between negative pi halves and pi halves. And that's just to let us know they're just looking at a portion of this graph to make it 1-to-1. so that it's okay for us to find the inverse. Also, this part here would be our domain of our original function, which means it will be our range of our whatever we end up with, our inverse function. So we can kind of keep that in mind. Right now, today, I'm just concerned with you finding the inverse function, not as so much the domain and range. All right, first step was what?
Set f of x to y.
So make it y equals 2 tangent x minus 3. We're following the same steps. Next thing.
Switch x and y.
Switch x and y. So x equals 2 tangent y minus 3. Solve for y. All right, so we say solve for y. What does that mean? What do I have to do here to do that?
Get y by itself.
Get y by itself. What am I going to do to do that? I want specifics. What am I going to do to make that happen? Have y on one side, everything else on the other. I'm not disagreeing with you all, but I want to know how to get there.
Add 3 to both sides.
Add 3 to both sides. That's what I'm looking for, okay? Tell me how to do this stuff. I want to make sure you know what you're doing here, okay? So tell me how to do it. So I've got x plus 3 equals 2 tangent y. Still, I don't have y by itself.
Would you take the inverse 2 tangent of y
Not yet.
and put it on x?
I got to do something else first. Divide by 2. Get rid of that 2 first. Let's get rid of 2. That gives me x plus 3 over 2 equals tangent y. Okay, so now we're at a place where we've got y as the argument of the tangent, but we need y out of there. We need it by itself. So now we want to do what you were suggesting and take the inverse tangent. And I like that you said that take the inverse tangent of both sides. Sometimes people want to call it doing other things. I'm not even going to say what words people want to use. But we are taking the inverse tangent. That's what we're doing, okay? So we've got to take the inverse tangent of both sides. So I didn't leave a lot of room to write it, but I'm doing that because of what we just looked at. If I do the inverse tangent of the tangent, they're undoing each other, right? And so I'll just get y out. But as the golden rule of algebra says, what you do to one side, you must do to the other. Do unto one side as you would do unto the other. Is that right? That's the golden rule of algebra. So we got to do that when we solve equations. All right, so what do we get here now? Inverse tangent of x plus 3 over 2 is equal to y. But we know that what we have here now is actually, that means that's going to be our f inverse function. Okay. That's our answer. That's the function we're looking for the inverse of f of x equals 2 tangent x minus 3. It's doing some algebra. You all like algebra, right? Some of you don't want to answer my question. All right, are we following the steps? We're going to try another one here just to get those steps in to find that inverse. Let's go down to number 60. F of x equals 2 cosine 3x plus 2. Negative 2/3 is less than or equal to x is less than or equal to 2/3 plus pi thirds. Again, they're telling me this part to make it be 1 to 1. That's what they're giving me for the domain of the function I'm working with. It would be the range of my answer, and I could find the domain of whatever I get. Right now, though, we want to find the inverse. First thing,
Change it to y.
yeah, y equals 2 cosine 3x plus 2. I'm just trying to be consistent and follow these steps, okay? Switch the x and y. Those parts are all good, right? Change f of x to y, switch x and y, that's not too bad. Now we get to the part where you all want me to solve for y, so how am I going to do that this time?
Divide by 2 first.
Divide by 2. That's to get rid of that 2 right there. Okay. So now I have x over 2 equals the cosine of 3y plus 2. What now? Do the inverse cosine of both sides, right? Take that inverse cosine. So now I have inverse cosine of x over 2 equals what on the right side? Just 3y plus 2. Do what with 2? Subtract 2. Good. Subtract 2. What's that going to leave me? I'm running out of space. Let's see. What do I get? Inverse cosine of x over 2, and then minus 2. Now I'm going to have to divide by 3. How am I going to divide by 3? It looks like a mess. Maybe I want to write it like this. Maybe it'd look better if I say that's 1/3 of the inverse cosine of x over 2 minus 2 equals y, or equals f inverse of x. I'll just go ahead and change it to equals f inverse. Okay.
Where'd you get 1/3 from?
Dividing by 3 is the same as multiplying by 1/3. Okay. Does that make sense? I just thought it looked better. I don't know. I could have left all that stuff over 3, but they mean the same. So this is how we find an inverse function. Maybe you've done this before with some algebraic functions in another class somewhere before now, like we did with y equals x squared. But we're doing it with the trig functions today. We also want to be able to solve some trig equations that involve inverses. And again, it uses algebra. So we're back with the algebra today. So let's look at a couple of equations and how we're going to solve those. Because you already were good telling me how to get y by itself. So I know you've got those equation steps down. So let's look at some here. Anything else on 60, number 60, before I leave that one? All right, let's go over here and solve an equation. Here's what the directions say. Find an exact solution, or actually it says find the exact solution. It's not like we had choices here. Find the, what's that? Yeah, it wouldn't be too exact then, that's right. What does it mean when they say exact anyway? We had a part on the test that said find the exact.
It means it needs to be a fraction.
Doesn't have to be a fraction, but a fraction is exact, yeah. What else?
Pi has to stay. We don't have to convert pi.
Means what?
We don't convert pi to
We don't convert pi to a decimal approximation. In fact, we don't convert anything to a decimal approximation. So if the answer is pi halves, the answer is pi halves. That's exact. If the answer is square root of 3 over 2, the answer is square root of 3 over 2. We don't want those decimal approximations because we want exact. Okay. Here we want to find exact solutions. Typically, when we talk about exact stuff, we don't want a calculator. Okay. Because we don't need the decimal approximations. That's an approximation. All right, we want exact answers here. We want to find the exact solution. When we solve an equation, we're solving for the variable. So here we're trying to get x by itself, similar to what we were doing when we were trying to find the inverse function, but we weren't solving them. We were finding another equation then. Now we're trying to figure out the value for x that would make this equation true. What are we going to do? Divide by 2. Good. So we have inverse cosine of x equals pi halves. What are we going to do now?
Take the cosine of both sides.
Now we've got to take the cosine of both sides to undo that inverse cosine. So we've got to take the cosine and take the cosine. What does that give me? X equals the cosine of pi halves, which we happen to know. What is the cosine of pi halves?
It'd be
0. 0 is the cosine of pi halves. Pi halves is your straight up, your 90-degree angle, right? Cosine is 0 there, the coordinates being 0, 1. You know, like when you take those little cell phone snapshots on your phone there, you want to take one of those in your mind of that unit circle. You got to have that to where you can think pretty quickly, you know, where's that angle pi halves? What are my coordinates there? visualize it. Work on visualizing that unit circle. So the answer here is 0. That is pretty exact. There's not much else we'll do with that. Let me give you one to try just a moment. I'm going to let you all work with one. Let's let you work with number 64. On 64, you have -6, inverse sine of, 3x, not x. -6, inverse sine of 3x equals pi. You're trying to get x by itself. Let me give you just a minute to try to do that. This is where we need Jeopardy music or something playing, don't we? All right, do we have an answer? Some of you have an answer? What answer do you have? One-third what?
Like in the brackets.
Like this? Is that what you're saying?
No, the other way.
What are you telling me here?
Kind of like what we did with the last one.
Just x equals 1/3, and then,
Yes.
You're going-
Sine.
okay, 1/3 sine what?
-5/6.
But wait a minute. Okay, I'm hearing the answer is x equals 1/3 negative, 1/3 sine negative pi over 6. You would know what the sine of negative pi over 6 was, so if that's what you're getting, you need to finish it out a little bit further. What do you say back here?
I got -1/6.
We got -1/6. What were you going to say up here?
I was going to say -2.
-2. This looks like multiple choice. Anybody else?
I got -1/6.
-1/6. What about you, John?
-3 square root of 3 over 2.
-3 square root of 3 over 2. Whoops. One of these answers is correct. So let's go through the problem. All right. What are we going to do first to get x by itself? Divide by -6. Okay. That's my first step. So I've got inverse sine of 3x equals -pi6. Take the sine of both sides. Take the sine. So that's where my sine of -pi6, I see where that's coming from now. The sine and the inverse sine on the left side undo each other, so I just get 3x equals the sine of -pi6. However, I know what the sine of -pi6 is. -1/2 is the sine of -pi6, right? So I can work with that. Then what? Divide by 3. X equals -1/2 divided by 3, which is the same as -1/2 times 1/3, which gives me -1/6. Okay? -1/6. Do you see where you made the mistake if you got one of the other answers?
Yep.
Or if you couldn't finish it? Do you see what was going on with it? I think it's helpful sometimes for you to work it out a little bit before I talk about it, though. Let's try one more like that. We have time for you to do another one like that. Any questions on this one? Okay, let's go to 68. Now this one looks a little longer. Go ahead, Brandon. You have a question? Okay, and I will save it. to the notes, but you finished? Okay. 68, 5 inverse sine of x minus 2 pi equals 2 inverse sine of x minus 3 pi. We want to get x by itself. This time, though, we have x's on both sides of our equation. We got to get the x's together on one side, everything else together on the other side. What are you going to do to start? You're going to do what with the 2 inverse sine of x? Subtract it. Okay, that works. Technically, you could start with any of these 4 terms. As long as you do the same thing to both sides of the equation, it's going to be okay. But she said to subtract this, so we'll start with that, and I'll let you finish it out. What do you think? 0? I'm hearing 0. I'll start my list over here in case I hear more than one thing. Maybe it's not going to be that long of a list, but what else? Somebody getting something else? Go ahead.
Negative square root of 3 over 2.
Negative square root of 3 over 2. Anything else? 1/2. Anything else? Should be negative square root of 3 over 2. Let's look at y. Okay. We have that 5 inverse sine x up here minus 2 inverse sine x where we were starting out. So that's going to give us 3 inverse sine x, right? And we start off there. So let's put 3 inverse sine x. Still have minus 2 pi equals, and we just have negative 3 pi now over there. Okay. What would we do next to get x by itself? Add 2 pi. Good. Add 2 pi. That gives me 3 inverse sine of x, just dropping down here, equals what? Negative pi. Good. What next?
Divide by 3.
Divide by 3. Good. So that we now have inverse sine x equals negative pi thirds. And what next? Take the sine. So that now we have x equals the sine of negative pi thirds. The sine of negative pi thirds is negative square root of 3 over 2. Okay. Questions on that one? Okay. Any questions on that one? The other thing that you were working on for today, I almost forgot, was you were working with your calculator a little bit to punch in some of these inverse functions, and also to work with some back from chapter 6 where we just punched in and had to decide if it was going to be, the mode should be in degrees or radians, but we used all the trig functions back in chapter 6. If we had something that asked for the secant, we had to do 1 divided by the cosine. Did anybody have a calculator question from either the problems from chapter 6, which were over on page 376, or from the problems on 446? Did anybody have a question from any of those calculator problems there? Go ahead.
Just a quick question. Like when it says sine 28 degrees, you want our calculator in degree mode, right?
Right. If it says sine 28 degrees, then definitely you want that mode on the calculator to be in degrees. If it says sine 5 pi 13ths, then we want the mode to be in radians.
What if you have like cotangent?
Cotangent of what? Anything?
Yeah,
25 degrees. Okay. On the calculator, we have to, there's no cotangent key. So we have to remember that cotangent is 1 over the tangent. So on the calculator, we'll punch in, just like I just wrote it, 1 divided by the tangent of 25 degrees. Again, you would want your mode there to be in degrees on that one. So if it asks for secant, you've got to do 1 divided by the cosine. If you did not try those problems, please go back and try those. They were on page 376, just so when we get to some other calculator stuff that we're going to use in Chapter 7, we want to know how to use those. 65 to 75 odd, practice those on the calculator. Anything else about the calculator problems? Just to make sure that you can get those to work out, that you know how to work with the mode on your calculator. Sometimes people don't know how to switch from degrees to radians. Make sure you know how. If you don't, ask me about it. Okay. Anything else on that last problem we did here? Anything else there? Some of you are still getting the rest of that. All right. I want you to practice some, of course. So I have some problems for you to practice with over on page, this is still section 7.1. We're on page 446. And I'm just going to list all the ones we should be looking at so far from 446 because I feel like some of you need to go back to the ones that I even assigned last Thursday. So no offense intended here, but I just want to make sure you know that you're looking at all these 13 through 67 odd. On 53 through 59, you do not have to give the domain and range because we didn't spend too much on that at this point. Just find the inverse. Okay. So only find the inverse. Anybody have a question there? All right. If you have any other concerns or questions regarding your test, anything like that, please do let me know. Otherwise, have a great day, and I will see you back on Thursday.